Keep hobbies.
Take about 30 more seconds to get your answer in.
So recently I went to go see my OBGYN.
Alright, so I will close in 5, 4, 3, 2, 1. Answers closed. Looks like most of you chose answer C. That is indeed the correct answer. If you happen to choose one of the other unlucky alphabet numbers, you can talk to me after class and we can clear it up to make sure that you'll definitely be able to do this on the exam. So the second clicker question then is, based on the action we did on Monday, now reading ahead to what we're going to learn about today, which one of the following is an orthopara director?
I don't know, I'm totally guessing now.
D might be ortho. Possibly.
What's a para director?
Yeah.
Well, she mentioned orthomesopara.
Alright, take about 30 more seconds.
Okay, it is D. Yeah. Probably A for the best. No, she didn't mention that. She didn't explain it at all. She was just like, you're
Alright,
reading about
got
that.
5, 4, 3, 2,
Okay.
1. Close it. So you saw that varied a bit. You know, that's okay because that's what we're going to learn about today, and I'll make sure to spend a lot of time on it. And if it's not clear by the end of the class which of these, why is the correct answer, then come see me. Don't forget I also have an office hour tomorrow from 3:30 to 5:30. Some of you stopped by yesterday. That was great, and hopefully more of you can come tomorrow. We can clear some things up. What was the answer? Oh, which one was the correct answer you'd like to know? Yeah, the correct answer was D.
I was gonna say.
I knew something. I remember
Alright, so different from Monday. So on Monday I did two things for the first time. One, I presented in front of the biggest audience ever. And two, I didn't use any notes or anything. I didn't use a computer or like a piece of paper. I just did it all from my brain. You guys are real troopers and sticking with me for that. And then today I decided to use half board and half presentation. Mostly because it's actually really difficult to draw on the board with this chalk, especially with such a small hand. It's terrible. So hopefully the artwork will be a little bit better on the PowerPoint presentation. Right. This shows up. Okay, great. So this is a quicker question. The answer is D. The brominated benzene ring is the only one here that's orthopara director. And we're going to talk all about today why that is and why the other ones are not. So if you go back to Monday, these are the 5 major reactions that we did. And they're really neat, but they're also maybe a little bit boring, right? We're creative people, and we want to further substitute the benzene ring and put all sorts of other substituents on there. And we need to figure out how to do that, and also how to do that in a controlled fashion. And so it turns out that each of these electrophile groups or substituents here, they have some say in how the second electrophile or the third electrophile is going to add on to the benzene ring. For example, a nitro group, I'll just point out, is a meta-director. So anytime you're adding on a second substituent with a nitro group, it's going to add to the meta position. Not only the flow. At any rate, I want to remind you that Friday we're going to do the same thing with clicker questions. We're going to do one review and one new. And so the material you need to read that's new is on page 740 through 742. I'm going to ask a question from that for Friday's clicker question, as well as a review from today. Okay, so first of all, why do we care about derivatizing the benzene rings and being creative with adding other substituents? Well, it turns out we get a lot of really important products from benzene. For example, epinephrine. If I said to you guys right now, put away your notes, take out a pencil, we're going to have a quiz, your heart kind of jumps, right? Your body's going to release a little bit of epinephrine because you're ready for that fight or flight response. Should I fight and take the quiz, or should I flight and run out the door not to take it? Also, BHT is a very common preservative we use to preserve foods, make them last longer. It can also preserve our chemicals that we use in the laboratory. Of course, there's ibuprofen that alleviates our Sunday morning hangover. I'm sure none of you ever have. But if you do, use ibuprofen, that's what the molecule looks like. And of course, there's vanillin too. And there's hundreds of others. These are just 4 examples of why we care about doing reactions with benzene rings. Okay, so on Monday when we did electrophilic aromatic substitution, all we did was take the regular benzene ring and we put an electrophile on it. And now today what we're going to do is take that electrophile derivative and we're going to add on another electrophile. And like I already said, the original electrophile that's here, it's going to direct how the second electrophile, or third one, adds. And it turns out they'll add in 2 different ways. It'll always be ortho and para, or it's always going to be meta. And then like I already said, just like it has something to say about where it goes on the ring, also how fast it goes on the ring. And that's the rate. So is that going to be activating or deactivating? And by activating, deactivating, that compares back to the original benzene ring. So if I were to brominate, let's say that benzene ring on the upper left-hand corner, and that reaction has a set rate. If I want to brominate this derivative, is that subsequent reaction going to happen faster, activating, than the original benzene reaction, or slower, deactivating, than the original benzene reaction? And really, what this all boils down to is there are effects, resonance effects and inductive effects. So you're not going to have to memorize every single functional group and whether or not it's going to be a meta-director or para-director, ortho-director, activating, deactivating. It boils down to resonance and inductive effects. So if you can understand these, you'll be able to easily identify which functional groups go where. My computer is also still sleeping. Okay, so let me show you an example. First, I wanted a table to show up. When it's ready, it will show up. But in the meantime, let's take, for example, aniline. It'll be benzene with an amine acid. Bromine group, I need to know whether this amine group is ortho-para-directing or if it's meta-directing. And there are two ways you know that it's ortho and para. One of those ways is if it's an alkyl group attached to the benzene ring, or if on the benzene ring you have an atom which has a lone pair of electrons that you can use to stabilize our carbocation intermediate. And in this case, the amine group has a lone pair of electrons which we can use to stabilize the carbocation, and that is going to go ortho and para. And I'll show you why that one's more stable. So if we make our electrophile, same thing we did on Monday. So I'm going to react this at the para position, so I'm going to use the pi pair over here. To form my carbocation intermediate. by now, you should feel pretty comfortable with being able to draw the resonance structures. So I'll draw mine, you draw yours, and then we'll talk about it. So hopefully you've gotten at least this resonance structure. And once I get here, you see that the carbocation is positioned next to the nitrogen substituent. And in this case, what I can do is take the pair of electrons here and switch the carbocation or the plus charge onto the nitrogen, giving me one of these resonance structures. Or from here, I could also form a third or a fourth actual resonance structure. So altogether, I have 4 resonance structures. Remember from Monday, we could only draw the 3 different resonance structures. But now we have a 4th one, which is this one. It's key to allowing this reaction to have a more stable carbocation. And with the more stable carbocation, you have a lower energy of activation. So this is going to be ortho and pair directing because it allows for this 4th resonance structure. Do you guys have any questions so far? Yeah.
Isn't that one at the bottom the same molecule as the one you started with?
This one here?
Yeah.
Same one as I started with over here?
Yeah.
Not quite, because I have over here the carbocation is in this location, and over here the carbocation is over here. So essentially, this carbocation is able to shift around the ring and be stabilized by the pi electrons. Any other questions so far? Yes.
So your end product doesn't look like a benzene, or does it?
So these are actually, it's a good point. So she's thinking that this is a product. It's not. It's just a resonance structure.
Okay.
They're just ways that we can push electrons around to try and stabilize our carbocation, right? The more we surround our carbocation with its electron density, the more stable that carbocation is going to be. These are all still resonance structures. So I guess before I show you what we would do if we did meta, I'll go ahead and finish the reaction. So let's just say it was this resonance structure right here we're going to react with. Remember, you have this, but you also now have iron FeBr4. And this will just come over and pick up the hydrogen, same thing we did on Monday. The pair of electrons between that carbon and the hydrogen will move back onto the ring to restore the aromaticity while simultaneously finishing the substitution. So that the product is a para-substituted benzene ring. So that's the total mechanism for this problem. So what I want you to do on your own time is do the same thing, but add the Br in the ortho position. And you'll see you'll also get 4 resonance structures that looks very similar to this one. So what I'm going to do now is show you the meta and why that one has a higher energy of activation, because the carbocation is not stabilized by the lone pair of electrons here. Where to draw that? I'll try to draw it here. So you take the same aniline starting material and Br2, FeBr3. Of course, you generate that strong electrophile that you guys already know how to do. And this time, I'm going to say, what if I want to then you'll see that the pi pair here can move over to shift the carbocation here. And you can also draw a third one. So you can do that in your notes, and I'll do mine on the board. So that's the second, and then the third. We have this can go here. Alright, so I have my 3 resonance structures. Hopefully you have the same thing in your notes. So if you notice, the carbocation went to this location, and then it shifted to the top, and then it shifted to the bottom right, but it never stopped at this location. And because it didn't stop here, the pair of electrons on the mean group is not able to donate its electrons or shift its electrons onto the ring like we did in this key resonance structure over here. So here we had 4 resonance structures to stabilize that carbocation. So since you had a more stable carbocation, you have lower activation energy, which allows this to be an ortho and pair director. This one has a less stable carbocation intermediate because there are only 3 ways to stabilize the carbocation. And so since it has a higher energy of activation, this was going to happen slower, so meta won't be preferred when you're using a aniline or when you're using an amine group, or really any group that has a lone or pair of electrons that you can put into the ring. I'm going to try my laptop again. Let it take a little bit longer. Eventually that table will show up. Is there any questions so far? How are you guys doing? Yeah.
I was just wondering, how come you added the VR to the, like, it was like 1, 3 instead of multiple?
Why I added the bromine
Yeah.
to the 1,3 position, like to this meta reaction,
Yeah. And then on the other one.
and then over here I did 1,4. Okay,
Yes.
so maybe I should actually take a step back and clarify the definition of ortho and meta and para. That might help. So anytime you add a substituent, or you have your benzene derivative and you want to add a subsequent substituent, if you want to add it in the ortho position, that's going to be here or here, next door to your functional group. And if it's going to be in the meta position, then it's going to add either here or here. And if you want to have a para, then you would add it in the 1,4 position. So it's just a matter of definition in the way I'm using words. So when I mean ortho para director, I mean that it's either going to add here, next door to my substituent, or it's going to add in the 1,4 position in the para position. And anytime I say meta, that just means it goes in here or here. Does that help to answer your question? Great. Yeah, I guess it helps to clarify that. Okay. All right, so if you think about it, there is also resonance and the inductive effect, right, on that slide I showed earlier, where both of those things play in on where it's going to direct and how fast the reaction is going to happen. So here I have a lone pair of electrons, but I also said that when you have an alkyl group, that's also an ortho pair director. But it doesn't have a lone pair of electrons to donate, right? So let me draw a benzene ring with an alkyl derivative. Let's say I have benzene with a CH3 group on it, which is formally, or a common name for that is toluene. We'll learn more about that on Friday. But for now, if I wanted to add Br2 or brominate this ring here, it's also going to be an ortho para director, because I've just told you that alkyl groups do. But the question remains why. And if we draw the resonance structures, I think it will be clear. So I'm going to do the same thing where we're going to add the Br group to the pair position, the 1,4 position. and then draw the resonance structures for that to show how stable the carbocation is. Okay, there's the first resonance structure. There are a couple more that I can draw. And one more. Alright, so hopefully you have the same three resonance structures in your notes. And what do you notice about each of these carbocation intermediate resonance structures? Anything particularly stable? Yeah.
What happened to the second methyl group?
What happened to the second?
The starting material. Looks like you have two ethyl groups starting each
No,
other.
just one. Just one methyl group. Yeah, just one. So, does anybody notice anything about these three carbocations that might make it more stable than the normal three that we draw? How about this is a secondary carbocation? What are the locations of the other carbocations? Yeah, we have a tertiary one and a secondary one. So before, like for example here, secondary, secondary, secondary. They're all secondary carbocations. And so even though we're learning something new with electrophilic aromatic substitution, all of the other organic chemistry rules still apply, especially when we're using these alkyl groups. And you know their tertiary is more stable. So because of the fact that I can form a tertiary carbocation here, this is going to be more stable than if I did meta. So if I did meta, I would get the same exact three resonance structures, except for this would be a CH3 here instead of an amine. And I would get secondary, secondary, secondary. So overall, those carbocation intermediates with the resonance structures have a higher energy of activation than this one because it's tertiary. Does that make sense? So that's why this one will direct towards either the ortho position or into the para position, and not so much on the meta position. Do you guys have any questions? Why don't you ask me? Yeah, what do you got?
That middle resonance structure, does it also count as allylic with the one that's tertiary?
The middle resonance structure does
It's
also
tertiary
count as allylic.
Or no, just tertiary?
Tertiary ethyl.
Just tertiary, I think, in this case. If it's not, I'll get back to you on that. Is that okay? All right. Any other questions? Yes.
Yeah, okay, so from the diagram that you had drawn, I kind of got the feeling that any of the five that we're studying can go through the orthopara or meta, but is it just that each specific one will either go orthopara or go meta? Like, it doesn't go either way?
Right, so it'll whenever you have those, it'll either go orthopara or it will go meta. For example, the nitro group is always going to add, the second substituent is always going to add in the meta position, always, across the board, 100% of the time. And when I have other groups that have lone pairs adjacent to the benzene ring or an alkyl group like this on the board, then in that case, it's always going to add either ortho or para. It's never going to go meta, ever, just because that energy of activation is higher. So why would it ever form in the meta position? Okay, well, the PowerPoint slide is not exactly cooperating, but if you look in your book when you get home on page 763, it's a really important table. It basically lists all the different functional groups here and describes whether they're ortho-para directors or if they're meta-directors. And not only if they're ortho-para-directors or meta-directors, but also if they're activating or deactivating. So that's on page 763. I did have it here, but it's got big sentences through it. So, turns out that you don't have to memorize all of the substituent groups, as long as you can remember that this is stabilized through resonance with a lone pair of electrons. And anything that has a pair of electrons will go ortho and para. Or anything that has an alkyl will also go ortho and para. And pretty much everything else will go meta and is deactivating. Yeah.
So the examples that we did were all para, but the same result would happen if we were to do ortho?
Exactly. And I challenge you to try that on your notes when you get home. So it's the same mechanism essentially. You're just going to attach it in the ortho position, and you'll see you'll get the same resonance structures, those 4 that I drew up there earlier. Okay, well, let's take a closer look then at sticking with the ortho and para and how many products you get, right? So if I said ortho or para, then you would expect to get a mixture of products, right? So your products would be, even though I just drew the para one up here, technically I would get ortho as well. And so if I have 2 positions that could react with ortho and one that could act para, you would expect that your product, which I actually haven't drawn yet. How about I finish this mechanism and then I talk about that product? Okay, I'll use this resonance structure. And if you take that FeBr4 from here, come over and pick up that hydrogen, same as before, and the pair of electrons between the carbon and hydrogen. Go back onto the ring, restore the aromaticity, and finish the substitution. Then your product is the para-substituted benzene ring. Right. So you might expect that even though I drew the para mechanism, you're also going to get ortho, and that's true. Right, so I'm going to get both of these products, and you might think that because I have 2 original locations where the ortho can attach at, then you would expect that this product would be greater, right? Something like 66 to 33 or something like that. Well, it turns out that's not the case. Does anybody have any suggestions to why ortho isn't going to be the most? Yeah.
Sterics.
Exactly. There's van der Waals interactions, right? So if I'm going to try to add something in the ortho position, these guys are going to undergo, or they're going to see van der Waals interactions. And so naturally, if you can go all the way on the other side, far away, you're not going to have the van der Waals interactions. So oftentimes you'll see that the para product is slightly larger than 50, it's the major one. That's not always the case. And there's other things that play a role in that is out of the scope of this course. But you can just remember that para is usually a major product, but you get both. Yes?
For when you're completing the reaction, do you use that middle resonance structure to complete it? The one with carbon para and tertiary?
So technically you can, but if I were to take this pair of electrons and put them onto a carbon, either or put them here or here, that's going to give me 5 bonds on this carbon or 5 bonds on this carbon. So if I wanted to use this resonance structure, I would have to go back to this one before I could actually do that. So does that kind of answer your question? In terms of the actual product, which one's more stable? I would think they're pretty comparable. It's forming that product because of the interactions that would be difficult. If that's different, then I'll let you know. Any other questions? Yeah.
You know how you said ortho could add either where you put it there or on top? Like
Yeah.
there are 2 places, so would both products show up?
Yeah. So you get both. Oftentimes you get both products to show up. And normally that would be a real pain because you have a mixture of products. But fortunately for these benzene rings, the difference between ortho and para are usually pretty different in physical properties. So you could distill, if they're liquids, both, or aqueous solutions, you could distill off one and collect them separately.
But so it wouldn't matter if for the ortho, like you know how there's 2 ortho products technically, so both of them would show up?
Exactly, yeah. So
But it wouldn't matter?
Because they're the exact same thing, right? It's a flat molecule,
Okay.
so there's no stereochemistry involved with that. Whether it's here or here, it's exactly the same.
Okay.
Yeah, it's identical. So I keep talking about resonance, but I also want to make sure to focus on the inductive effect, right? Because if you have just a regular benzene ring, right, it has all hydrogens coming off of it. So I'll just draw one. You can imagine the other even for example, nitrogen, it's going to be pulling electron density from the ring. And I just told you this is activating because it can donate its electrons right here, but actually it's electron withdrawing. How would I show you an example of what's called anisole, which is methoxybenzene? Okay, so if I have methoxybenzene, or anisole as its common name, definitely the oxygen is a lot more electronegative than that hydrogen. So it's going to be wanting to pull electron density away from the ring. And when you're trying to decide whether a reaction is going to be activating or deactivating, you have to consider both the fact that whether it can put its electrons here, as well as how much it's pulling its electrons away. Now experimentally, we know that this is an activating reaction, and it's going to go orthoperic because we get experimentally. So in that case, the electrons, they're able to form here, just like in that ring before. Let's say if I draw a resonance structure. Right, that's assuming that the whole reaction I did before is exactly the same. And this is one of those 4 resonance structures, the special one that allows us to have the more stable carbocation intermediate. The fact that it can do this outweighs its electron withdrawing effects. There are other cases though, let's see. Well, are there any questions here? I'm going to talk about meta. I'm going to switch gears a little bit.
So what you're saying is that that's normally an orthopara director, but it goes meta? I'm sorry, I kind of lost
No,
me.
that's okay. So it is normally an orthopara director, and it will always go orthopara. Always. Should I draw the mechanism for that?
No, I just didn't know what you were trying to
Okay.
say.
Alright, well now let me shift gears and talk about the meta, and then maybe it will make some more sense. So if ortho and para is something that has a lone pair of electrons that is adjacent to the benzene ring or an alkyl group, then the meta directors must be pretty much everything else. Let's take a nitro group for example. Actually, I should write that out so it becomes more clear. So you know the nitro group looks like this. Okay? Let's say I want to do a subsequent reaction with this by adding a bromine to it. You know how to form the carbocation intermediate? I mean the strong electrophile? So I've drawn this one differently than I drew the other complexes with iron tribromide, but know that they're the same thing. Because what's going to happen is a pair of electrons will come over here and pick up the Br. Let's say for a second I don't know whether nitro is actually a meta directing or if it's an ortho-para directing. And since I don't know, I'm going to pick it where it goes. I'm going to have it go onto the para position. Python's there. Put the Br in the para position. Nothing's happened to that hydrogen, so there's my carbocation. So if I want to draw my resonance structures now for the carbocations, watch what happens. Take this pi pair here, move the carbocation up. Wow, so what does that look like? Good news or bad news? Yeah, some bad news, right? You don't want to put 2 positive charges next to each other. That is way too high in energy, not good. And even though this can continue to draw on the 3rd resonance structure, enough to just ruin it. So even though I can have the 3 resonance structures, this one is such high in energy that it's not going to want to form a para product. And if you draw in your notes on your own time, you do the same thing with these similar resonance structures, albeit with the bromine on the ortho position. So that's pretty high in energy. So if I try to put it in the meta position now, let's check the resonance structures. I'll draw that up here. So we have the same thing. These are plus. Now I'll take it from over here, and I'm going to add the VR into the meta position. Okay, so then you actually have the same thing in your notes as a carbocation intermediate. And if I try to draw those resonance structures, this pi pair can go over here, put the carbocation here. Then you can move the pi pair again to make your 3rd resonance structure. Okay, so if I had added the BR to the meta position that we've done up here, I formed 3 carbocation intermediates, but this time the carbocation skips over this middle position. It goes here, then it goes here, and then it goes over here. So if you were to add a BR to the ring, it would be having a lower energy of activation if you were to add it in the meta position, because even though carbocations aren't stable, these carbocation intermediate form is more stable than this one over here because of this. That's why things like nitro groups are meta-directing, and that's why they'll add to the meta position. So anything that actually has a positive charge on it, or some sort of polar effect, right? It doesn't actually have to be a full positive charge. It could be something that even has a dipole. So if I put an acyl group on there, remember the carbonyl group with the carbon coming off of it? So even though this carbon has the same molecular negativity as this carbon here, you have a dipole moment, right? If you look at the oxygen, it's more electronegative. So you have a dipole moment this way, which causes a partial positive charge on that carbon. Which, when you do this same reaction using the acyl group here, and let's say if I plug that over here, the nitro group instead, do the same mechanism, just replace it with that acyl group, I'm going to run into that same problem with that positive carbocation intermediate is going to be right here. And even though that's on a full charge, those positive charges aren't going to want to be by each other. So this also is going to be a meta-director. And it's going to be deactivating. It'll happen more slowly than if I had done the reaction without any substituents on it at all. Yes?
Is the same situation true for like carboxylic acids?
Yes.
Okay.
Yes, it is. Yeah. So if you have a pair of alone pairs you can donate, like that amine group, alcohol group, anything with a lone pair of electrons attached directly to the benzene ring, that'll be ortho and para, and it will be activating, which means it will happen faster than with benzene alone. And then anything else was going to be meta-directing, and this is the reason why, because of this resonance structure here. Even if it's on a full positive charge, even if it's a partial positive, they're not going to want to be by each other, and so they're going to be slower than a reaction with regular benzene would be alone. Do you guys have any questions? Yeah.
So is meta always deactivating?
Actually, yeah. In all cases, meta is always going to be deactivating. And it turns out the nitro group is the most deactivating. It'll make a lot more sense when you're able to look at page 763 in your book of that whole entire table. You'll see that all the ones that are activating at the top of the table all have lone pair of electrons, or they're like an alkyl group. And the ones at the bottom of the table are all having some sort of positive charged character here, even if it's a partial positive. And those are all meta and all deactivating. And yeah, I think I have a couple more things to talk about, but first, is there any questions about what I've discussed or anything that's kind of a little cloudy? So it all makes sense? Yeah. Okay, that's what I wanted to say. Thank you. I'm glad you asked. So there's actually one case where an ortho and para director is deactivating. Does anybody know what case that is? Exactly, said that. Yeah, she's exactly right. So if I am doing a halogen, if I am using a halogen, let's say I'll switch. I'm sick of. I'm gonna change it to a CO. So you all know that CO has lone pair of electrons that are next to the benzene ring. So it's going to be an ortho pair director. But it doesn't have that fourth resonance stability, right? Because you're not going to put a double bond with the chlorine. That would be bad. That doesn't happen. So you don't have that resonance stabilized effect. So even though it is better for it to go ortho or para, it's going to be slower reaction. So it's going to be deactivating. So it'll still happen ortho and para because of these, but it's just going to be a little bit slow. So that's one case, or pretty much the only case you guys will hear about in this class, where ortho para director is deactivating. In all other cases that you guys will learn about in this class, ortho and para are always activating. How about some other questions? And alright, so we have like another 6 minutes left. Should I do some more reactions on the board? Or should I talk about the pair more? What was that?
Whatever the clicker questions.
Whatever the clicker questions are going to be. So let's see. For Friday's clicker questions, you know it's going to be on page 740 to 742. If you haven't looked at your book yet, that's nomenclature. So there are going to be questions on naming. And in terms of the question for review of this work, I would probably ask you something like, is this a meta director or is this an ortho para director? So if you can identify, what constitutes a meta director or an ortho para director, then we would be just fine with that. And I know there's one other thing that I need to say, and I feel like to throw my computer across the stage. You guys want to see that? That's what I feel like to do. Because I know there's something on here I want to tell you guys, and I'm just not remembering it at the moment. Let's see. Talked about that ortho and pair, you're going to get usually a greater pair product. And I talked about what makes ortho and pair and what makes meta, and that's deactivating. And yeah, that's all I can remember. Okay, so we'll be finished. And if you guys have questions, I'll hang out here